This is part 2 of section 313233 video. So in part 1, we filled out this table, and I'm just going to very quickly just put in what we had. And continue on with the next question. So what we're going to do here is we're going to graph these ordered pairs, these points. So we're going to choose a scale, a beginning and end, and a scale for the vertical axis. But before we do that, I just want to talk about how we know what numbers are in the horizontal axis and what in the vertical. Most of the time, when we make a graph, the independent variable will go horizontally on the graph. And then the outputs, the dependent variable, will go on the vertical axis. So if I look at my points, we start with 0 as an output, and then we go to 1. So I'm at the very least going to have to fit 0 to 1 on the graph. To choose a scale, probably the best way to go about that is to look at what is the change in my output values from term to term. So from output to output, it looks like I add 0.25 each time. So 0.25 would probably be a good scale to use. So let's make our beginning 0, our end, let's make that 1, and our scale, let's make that 0.25. Okay, so we're going to plot these points, but before we do that, let's go ahead and finish labeling this graph, probably put a title on it, and we're talking about here in this problem cost of text messages. I'll just call that cost of text because we all know what that means. The vertical axis is that cost, and that is in dollars. And the horizontal axis is talking about how many texts are sent. Now the scale on the horizontal axis will be going by 1, because that's what we go by in our independent variable, and we chose our vertical axis to go by 0.25. So we'll plot these points. We have 0, 0, 1.25, 2.5, 3.75, and 4, 1. What do you notice about these lines, take it away for a second, these points here? They make a line. We call that a linear function. And the data points together make a line. Okay, so there we go. That's what it would look like. Let's go back to function notation here for a minute and see how we could represent the cost of sending 15 text messages with function notation. Well, they call this function C of M. This right here, and this is the function rule on the right side. So what I can do if I want to figure out how much it would cost after 15 text messages is put C of 15 and replace 15 for M. So do 0.25 times 15. And I believe if you do that, you get $3.75. So that's how much it would cost to send 15 text messages. That's pretty expensive. Now suppose we don't limit our domain or our independent variables to 4 texts. I mean, most people nowadays, they send quite a few texts in a day, especially you teenagers in high school send lots and lots of texts. So it's good that now most plans don't charge per text, but just, you know, most plans have an unlimited text. So the reasonable domain for this function, I mean, obviously there's a set end number of text messages that one person can send. You can't send probably one text message more often than one a second, or I don't know. But we could just say that our domain are all positive whole numbers. It's also called natural numbers. If you say natural numbers, that also means positive whole numbers. But what about the range? My range, which are my dependent variables, my outputs, are not whole numbers. Because see here, for this point, it's 0.25. They're here, 0.5, 0.75, 1. Those are not whole numbers. But what they are multiples of my scale, multiples of 0.25. So if I said positive multiples of 0.25, that would be my range. So say you sent 100 texts, that would cost you $25. 25 is a multiple of 0.25. Okay? So we already talked about this. The independent variable is represented by the horizontal axis. Okay, it's convention. It doesn't absolutely have to be that way, but it's just the way we're used to it. So I'm not going to really talk about why does this make sense. It's just the way we do it. But this next question is interesting. Would it make sense to connect the points on the graph with a line? Why or why not? So right now we have isolated points. In order to connect these points with a line, that would mean that I could send half a text, or a quarter of a text, or 0.13 of a text, and that doesn't make sense. You can only send a whole text message. Even if it's just a smiley face, that is one text message. So I can't connect these dots, and when you can't connect the dots, it is called a discrete function. Discrete means individual data points. The opposite of discrete would be continuous. Continuous would be a function that we could connect the dots with a line. So keep that in mind. So this would be no, because you cannot send a part of a text. Okay. All right, not going to go into detail too much about this right here, just reminding you that when we do a function, we have an input, we perform some kind of a rule or operation upon that input, and then we get the output. So in this case, one text message would cost 25 cents. But suppose that they change the cost of the text message and it was 20 cents a text message rather than 25 cents. Would that change the domain of the function? No, you're still sending whole number text, so that will still be the same. But the range will change. They will no longer be multiples of 0.25, but multiples of 0.2. I guess I should also include in there positive, because we won't have a negative cost. That doesn't make sense. Okay, so far what we've talked about is a function is for every input there is only one output. And we've talked about function notation. We can write a function rule that shows what we do with our input values as something like f of x, say we multiply by 2 and then add 1. Okay, that's a function using function notation. And then we also talked about Discrete versus continuous. Discrete means I can't connect the dots. It doesn't make sense in the context of the problem. Continuous means I can connect the dots. I can have values in between or an infinite number of possible values. So on your homework, you're going to have to be able to distinguish between discrete and continuous. Let's take a look at these examples. Here we are determining whether each pairing of numbers describes a function. If so, identify the domain and range. If not, explain why not. It says for number 1, each whole number from 0 to 9 is paired with its opposite. Opposite just means if it's positive and negative. If all these numbers are positive, each number has its own opposite. So this is a function. So the domain would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the range would be the same thing, just negatives. Although 0 doesn't have a negative of itself. It's just the same value. So there we go. Each odd number from 3 to 9 is paired with the next greater whole number. So let's think of an example. The number 5, that's odd. Is there only one number that is the next greater than 5? There is. It's just 6. So that means that this is a function. So the domain would be 3, 5, 7, 9. The range would be 4, 6, 8, and 10. All right, number 3. The whole numbers from 10 to 12 are paired with their factors. Here we come across a problem because 10, for example, has more than one factor. 10 actually has 4 factors, 1, 2, 5, and 10. So this is not a function. 10 has 4 outputs. So that fails the definition of a function. How about this one? Each even number from 2 to 10 is paired with half the number. That's also a function. I'm not going to do the domain and range here because I think we got that figured out. Each number only has 1/2 of itself. It's not like if I take the half of 2, I'm not going to get 2 different answers. It's just 1. Number 5, this is written a different way. Here we have a set of ordered pairs. The first values in the ordered pairs are the independent variable, the inputs, the domain. If I look, I see 36 listed twice. Now, if I have the same output, the second value the same, then we're okay. But if we look, they are not. They're different numbers, so this is not a function because we have more than one output for an input of 36. But in number 6, if you look, all of our inputs are different values. Sure, I've got negative 64 and positive 64, but that's okay. They're different values. So each input has its own output. This is a function. And if we were to list its domain and range, the domain would be all those numbers that I circled, and the range would be all the other ones. Okay? So again, what I want you to take away from this section is the fact that we can use function notation, f of x. And in order to be a function, for every input there is only one output. And there are different types of functions. Functions we call discrete, meaning isolated points, or continuous, connected with a smooth line or curve. Continuing with this idea of functions, we're going to use function notation here in this section, but we're also going to perform different operations with the function. So we are given f of x equals 3x minus 1, and g of x equals 2x plus 2. So what we're supposed to do is add those two functions together. So we will take the function rule of each function and we will add them together. In order to do that, we would combine like terms, group them together, and get x plus 1. Now this function, since I've added the two other functions together, has its own name. F, G, and H are the most common letters that we use. So here, after I add functions G and H together, F and G together, then I get a new function called H of x. So that's adding. Subtracting is very similar. You just have to remember you are subtracting each term. So if G of x is 4x minus 2, taken from right there, then when I combine like terms, it'll be x minus 4x, and then 5 minus negative 2. Minus and negative will turn into plus, so this will be negative 3x plus 7. Again, that's h of x. Okay, so pretty simple, as long as you understand what the function notation is saying, what it means, and if you can combine like terms and do simplifying like that. Multiplying is the same. So if f of x is 3, we'd multiply 3 times g of x, which is 1/3 x minus 2. Distribute the 3, we will get x minus 6. Make sure when you distribute to every term inside the parentheses. Okay? For this reflection question, we're going to talk about the two functions that we used in part A. So 3x minus 1 and negative 2x plus 2. If I were to plug in certain values for x, so for example, down here in the table, if I were to plug in negative 2 for f of x, I would get negative 7. And if I were to plug in negative 2 for g of x, I would get 6. So if you add those two values together, you get negative 1. Well, if I were to take that same input, negative 2, and plug it into the function that we created after we added f of x and g of x, I should get the same answer. Negative 2 plus 1 is negative 1. Well, that's what we got here. So all this is saying is that when I add two functions together and create a new function, I can plug in the input, whatever input I choose, and it should be the same in that function as it would be if I plugged it into each function individually and then added them. So this would be 0, 1, 2, 3. Okay? So what do we notice? We notice that the answers that we get for f of x plus g of x will get me the answers if I plug the input into h of x. Okay? Now this person, using the same two functions that we just talked about, instead of getting x plus 1, they got 5x plus 1. So they got a different answer than we did, but when they put in x equals 0 for their input to check and make sure they got the right thing, they did get the same for f of x plus g and h of x. They got the same output value. So they thought, I got the right answer. But, if you look here, we got x plus 1. They got 5x plus 1. Where do you think they got the 5x? Well, they probably didn't carry the negative with the negative 2x, so they didn't combine like terms correctly. Okay? All right, let's see what this looks like in an application. So it says, for the initial year of a soccer camp, 44 girls and 56 boys enrolled. Each year thereafter, 5 more girls and 5 more boys enrolled in the camp. Let T be the time in years since the camp opened. Write a rule for each of the following functions. G of T is the number of girls enrolled as a function of time T. B of T is the number of boys enrolled as a function of time T. Capital T of T is the total enrollment as a function of time T. So let's start with the girls. So function G of T, the initial value is 44. And the rate at which the girls are changing is 5 more girls. So I could write this as 44 plus 5t, 5 girls per year. And the boys start with 56, and they are growing by 8 more per year. So I could write this as 56 plus 18. So if I take these two functions, g of t, 44 plus 5t, and b of t, 56 plus 18, and add them together, then I should get the total enrollment. 44 plus 56 is going to be 100. 5t plus 8t is 13t. So my total enrollment function would be 100 plus 13t. Now when they say use unit analysis to show that the rule for g of t makes sense, for g of t that's just the girls. Okay, well, if I have 44 girls plus 5 girls each year times the number of years, what unit cancels? Year. So that means at the end I'll have a certain number of girls. So depending on how many years you're looking at, 2, 3, 4, whatever, what have you, the years will cancel and we will just have a value of girls left. Okay, this next part is interesting. It's how we can create a function based off of finding the inverse of a given function. An inverse of a function is another function that undoes everything that the original one does. So if I look at this function here in example 4, 2x plus 1, what's happening to that function is multiplying by 2 and then adding 1. So if I chose, say, an input of 3, x is 3, I would first multiply 3 by 2, get 6, and then add 1 to 6 and get 7. So if I have f of 3, my output will be 7. Well, if we do the inverse of that, basically what that means is that I should be able to take 7, the answer that I got, do the operations backwards from what we did, and get 3. So the operations backwards from the original function would be to subtract 1, then to divide by 2. So if I take 7, subtract 1, we get 6. If I take 6, divide by 2, we get 3. Well, 3 was the input value. I could also write this in function notation. Now when we write the inverse of a function, we can no longer use the name that we gave for the original. So if the original was f of x, we have to come up with another name. And again, very commonly we use g or h. Here we're using g. So to do those operations backwards, multiply by 2, add 1, we would do subtract 1, divide by 2. So my inverse function would be x minus 1 over 2. And if I put in 7, as an input value, I would get out 3. So if f of 3 equals 7 and g of 7 equals 3, essentially what we are doing is we are switching the x's and y's, the inputs and the outputs. Now when I use the word y, or the variable y, just as x is very commonly used for that input, y is very commonly used for that output. So in this table, they listed inputs and outputs for function f of x. If we are switching the inputs and outputs, then g of x, if I complete the table, would look like this. That's how inverses work. It doesn't matter what the input and output is. If I find the inverse, then I will switch the inputs and outputs. So if f of a equals b, then g of b should equal a. If I say that g of x is the inverse of f of x, could I also say that f of x is the inverse of g of x? Absolutely. It doesn't matter which way I switch my inputs and outputs. If I go from g of x to f of x, that will work. If I go from f of x to g of x, that works also. Because both undo each other. Okay, so that's how inverses work. What we're going to do on the next page is we are going to find the inverse of a certain function. Now, what they're going to show us here is instead of using the function notation f of x, let's replace it with y. The only reason for that is because it's easier to use one letter, y, when we're solving the equation, rather than using 4 symbols, f parentheses, x parentheses, just to save time. But what you have to remember is at the very end, after you find the inverse, it is no longer the same function. So you have to give it a different name. Again, we're just using g of x because that's what's common. So here in this problem, what they do is they first replace the f of x with a y. Again, it's just only for convenience. You could technically leave f of x in there. The only issue is you have to rename it. You have to make sure that you give it a different name at the end, because they're not the same. Okay, so what I'm going to do is I'm going to solve for x. I'll add 1 to both sides, multiply by 2, distribute. The reason why we solve for x here is because in the next step we're going to switch the x's and y's. Because again, in an inverse you switch the input and the output, the independent variable and the dependent variable. So if the function f of x equals 1 half x minus 1 is the original function, the inverse g of x would be 2x plus 2. Now notice the result. In the problem that we did earlier, it was a little bit more intuitive. It was a little bit easier to see what it would be without doing this process. But now that you know what an inverse is, it's best to do it using this process rather than trying to think about it mentally. Okay? So, before we do maybe some of these reflection questions, we'll do the ones at the end. I want to do another example. And I'm going to do it a little bit differently than how they did. So let's say this is my function, f of x equals 3x minus 7. And I want to find the inverse. I do go ahead, like they do, replace the f of x with y, but I switch the x and y first. And then I solve, but I solve for y. What they did is they switched the x's and the y's at the end after they solved. Doesn't matter which way you do it. This is just the way I was taught, so this is how I tend to do it. But if you want to wait to switch until the end, there's nothing wrong with that. But what I would do is I'd add 7, get x plus 7 equals 3y, divide by 3, and there's my function. But I'm not going to say y equals. I'm going to have to name it using g of x. Again, you could use h of x, you could use another letter, but g is the common one. Okay. Now I'm also going to show you something very interesting about how inverses work. This is one way that you can check your answer. If you take one of the functions and you put it in as the input in the other function, I need big parentheses here, you'll find that something interesting happens when you simplify. The 3's here cancel, and you get x plus 7 minus 7. The 7's cancel, and you're left with just x. If you were to do it the other way, where you put 3x minus 7 in for the x here, you should get the same thing. So I would do 3x minus 7 plus 7 and then divided by 3. The negative 7 plus 7 cancel. The 3's cancel, and you're left with x. So no matter what you put in, so if you go from g of x to f of x or f of x to g of x, doesn't matter. Both times you simplify and you find x. This is called composing functions, or putting a function inside of a function. So if you get your answer and you want to check your work, this is one way that you can do it. You just have to be sure you take the whole entire function and you replace the x in the other function with that. And then you use your correct order of operations from there. Okay? Well, let's continue on with this conversation over here. So, to find f of 4, it says, no, not to find it. Find f of 4. So let's put 4 in for x. Half of 4 is 2. 2 minus 1 is 1. So f of 4 is 1. Then we will take this output, 1, and put that in to g of x. That would give me 2 times 1 plus 2. So g of 1 equals 4. Does this make sense? Yes, it does, because we've talked about what inverse functions are. It switches the x's and y's, the inputs and the outputs, and that's what's happened here. Now, when we talk about using an inverse operation, when we got rid of the 1/2, we multiplied both sides by 2 instead of dividing by 1/2. So instead of using the inverse operation for multiplication division, we used what we call a multiplicative inverse. Why is this acceptable? Because multiplying by a number's reciprocal is equivalent to dividing by the number. Okay. All right. We're going to skip 5C. We're going to talk about this. This is something very interesting that happens with inverse functions. So f of x is graphed. They also want us to graph y equals x. So if x equals 1, y equals 1. X equals 2, y equals 2. X equals negative 1, y equals negative 1. X equals negative 2, y equals negative 2. So we've got this line going through the center of my graph. Perhaps I should maybe do that with a different color. Then they want us to graph g of x. G of x was 2x plus 2, if I recall. Yep. So 2x plus 2, this may be a bit of a review for you guys, but one way that I can do that is I can graph the 2, the constant, plus 2 as the y-intercept first. And the 2x, the 2 in front of the x is the slope, the rise over the run. We go up 2, right 1, up 2, right 1. We could also go down 2, left 1. And I could continue with this as long as I want to. So then here's my straight line here. What do you notice about the blue line and the black line? It is reflected over the green line. If I were to take this point here, 1, 4, on this line, it would become 4, 1 over there. Switch the x's and y's, and that's exactly what 5e is talking about. The corresponding point on the graph of g would be switching the x's and y's, 1, 4. So if AB is a point on the graph of f, the original function, the corresponding point on the graph of g will be BA, switching the x's and y's. So that is the inverse of a function. So that's the end of this video. This is your assignment. All of the assignment comes from worksheet pages from your red workbook.